Okay, so I'll take it from where we left it last Monday. And so I wanted to complete this first and then say a bit more about zoning and fielding. And finally, we do something else. Eventually. We get bored with one topic, we skip to another one. So, I told you the idea behind clustering, which is very popular, not just in search engines. And it was the following. I mean, I call it clustering because in some sense, as I was telling you last time, it assumes more or less that in the vector space, there is some clustering of the documents according to topic similarity, right? So, I mean, makes sense. Doesn't have to be the case, but that's very often the case. So, what is the idea behind this? It is that if you have a picture like this, you sample a subset of points of documents, which we call leaders. Normally, something in the order of square root the number of documents is a good choice. And then, essentially, you do the following. You associate every document to the closest leader, to the nearest leader, and then whenever you get a query, the query is just compared in terms of cosine similarity with the leaders. Once you have found the nearest leader, you just return the followers of that leader. Very simple. Now, why this idea? Why square root of n? I was telling you square root of n comes actually from some theoretical considerations. It allows you to have a decent sampling of the underlying distribution of the points in the feature space. Can anything go wrong here? Yeah, I think I showed you. I mean, for example, what may happen is that you miss one of the top K documents for the query, right? I mean, I have to say this is something you cannot really avoid. Clustering, as you will see in the future, perhaps, is not an easy problem to deal with. And actually, it's very, how should I say? It is still pretty hard for a machine to be able to reproduce for what the human eye is so good at doing in 2 dimensions. Okay, I look at this and I see 1, 2, 3, 4, 5 clusters of points, right? If you want a computer to do the same, well, probably in this case, it will be able to do this. But in general, there may be cases that are quite obvious to the human eye, but very hard for a machine to discern. Okay, I mean, it's a complicated problem. Now, there are variants of this scheme. In general, in order to improve robustness and accuracy, what can you do? One thing you can do is the following. You could decide that, for example, every document is not just a follower of one leader, but, for example, of the 3 closest leaders. Okay? This gives you a bit more flexibility, and it also expands the subset of documents that you will return in response to a query. Another thing you can do is that instead of, when you have the query, instead of just looking for the closest leader, you look for, I don't know, the 2 closest leaders, and you collect all their followers. Again, this will improve, as we shall see, recall. So the number of relevant documents that you should collect and that you actually collect. Okay, we actually saw that counterexample. So now something which has to do, just to close this part, on let's say cosine similarity computation. One last point, as I was telling you last time, I think. So a document, very often, in particular a web page, is something that is semi-structured. So it means that it has some areas with different, how should I say, meaning. For example, it may have a title, it may have an order field, a date, or whatever. All this information actually, so called metadata. Yeah, metadata information can be very, very rich semantically speaking, and this richness should be leveraged. So how can you do that? Well, you can do a number of things. First of all, if you look at, let's say, metadata, actually there are two types of, how should I say, substructures in a document. Some of them, we call them just fields. For example, order is a field. It's just in the sense that it is an area of the text that will just contain a limited amount of information, and you know what to expect, a name, okay? A date, likewise, is something where you know exactly what to expect. Other things are less, how should I say, can have an arbitrary amount of text. For example, the title, I mean, it's never going to be, I don't know, more than a few hundred bytes long normally, but it has a variable length, for example, and so on. So you can leverage all this information in some sense. Just to distinguish between fields, like I was saying now, and areas of the text that actually have not a predefined maximum length. For example, we speak of zones. For example, a title could be a zone. An abstract is a zone, right? It's just a short summary of a document, and you cannot predict its length. It may not even be there, or it may be very long. Then it's not an abstract anymore, perhaps, but some people tend to be lengthy when they speak. So what can I do? How can I leverage this information? So you can handle with this information separately. For example, in principle, you could define inverted indexes for each of these fields or zones, right? So having something like this. For example, you have a name, William, and the name may appear in different parts of the document, and for title, abstract, body, and so on. And for each of them, you will keep a separate posting list. That's the idea. So William will appear in the abstracts of documents with doc IDs 11, 121, and so on. On the other hand, how do you encode this in practice? Very often you're not going to build a different posting list for each possible role of a term. Normally you embed it within the posting list associated to that particular term. For example, having fields in each entry, in each posting list entry, okay? So for example, William appears both as order and in the title of document 2 and so on, okay? So, once you have done this, you can at that point start to take the different roles of a term within different areas of the document into account. For example, you may have different ways of scoring documents with respect to terms depending on where the term appears in the document. If, for example, a term appears in the title of the document, the term may receive a considerably higher weight for the document, okay, and so on. So there is a number of schemes you can adopt. I warmly invite you to check these parts on the book. I'll give you the full references, the relevant chapters, and so on. Please, I remind you, don't study on the slides. Go through the book, okay? The last thing we can, actually we already mentioned this, is the idea of having tiered indices. Actually people write indexes now, but it should be indices anyway. So why are tiered indexes important? Because this has to do a little bit with champions list, you remember, with the ideas of having essentially posting lists that perhaps are shorter but contain documents that are more likely to be relevant for queries. And how can you build these postings, these special indexes, by, for example, using some static measure of relevance, or of authority, if you want, like this famous GD, no beta specified, that perhaps will be specified at a later time in this course. And then you will have something like this. So notice that typically when you have several tiers, a possible way of proceeding could be to have the same document for a given term to appear only once. So for example, there will be some documents that will have higher weight with respect to some term, for example, insurance, and then they will appear in tier 1. And in tier 2, there will be another subset of documents associated to the same term with smaller weights and so on. So you normally start with the first tier, try to acquire enough documents to answer the query, and if you haven't, you jump to the second tier and so on. Okay? I'm just mentioning it here, actually. Sometimes you have different tiers just because that's the way you organize your documents. So for example, you could have different posting lists in general you have different posting lists for every term, right? What you could do is, since posting lists are very large, and nowadays it's common practice to keep them in the main memory of a machine, it's easy to have a posting list that perhaps does not fit main memory, right? So what can you do? What you can do is to have sort of a front-end machine which receives queries, and then these queries are submitted to different machines. What does it mean? For example, so you could have each machine host the posting list of a subset of the terms. Okay? And then whenever you get a query, for example, containing the term terms T1 and T2, what will happen is that you will retrieve posting lists you will access posting lists for these terms from two different machines in parallel this time. That's very efficient. That's why you do it. So how can you split the terms between, how can you decide an efficient way of splitting the terms between different machines, you know? So that more or less the amount of memory needed on each machine is the same. You can use for example, a hash function, right? Simply a hash function that is going to hash terms on two the machines. More or less, you will have, if a hash function behaves decently with respect to randomness, you will have that more or less, you will have the same number of terms on each machine, and the total length of the posting lists on each machine will be roughly the same. Okay? With exceptions, of course. But and this is another idea which has to do with tiering. So this was just to tell you that actually it doesn't have to be that way. I mean, these are more or less architectural choices, but there is a lot of variance you may consider depending on your requirements, depending on the resources you have available and so on. So this very same idea can be used in a different way. Okay? Okay. So another issue which you have with search engines typically is that, for example, when you submit a query here, you issue what is called a phrase query. So it's just a bag of words, right? That's a phrase query. Now, what is the search engine going to do? For example, what was I looking that I was unable to find? I don't know. Coffee, bar, yeah. I don't know. I hope I am not redirected. Yes, that's what I meant. Good. Now, sometimes, well, it is not the case for this query, but more or less in these pages, all the terms appeared in each of the documents that I returned, right? But sometimes not all of them appear. And then you notice, for example, you will notice something that tries must include these terms, includes a subset of the terms. So it means that actually the search engine, upon receiving a query, is pre-processing it in some way. What is it doing? So first of all, for example, the search engine will actually issue a query of the form, I don't know, coffee and bar and near and piazza and Vittoria. So you want all the terms. Eventually, if the result set is not large enough, it will expand it by, for example, allowing for some of the terms to not be present, okay? At that point, you have to decide, for example, on which basis you are going to drop a few of the terms. One idea can be, for example, measuring the importance of terms present in the query on the basis of their inverse document frequency, to make an example, okay? Or other techniques. But just to make you aware of the fact that actually this is not exactly what the search engine is going to process. I mean, yes, but also there is a lot of pre-processing within 0.5 seconds going on. Yeah, and this is, if you put everything together, then this is more or less the picture. And most of these blocks you have seen with me or with Professor Vitaletti, essentially, right? So indexers means what we have seen so far, essentially. Metadata, inexact top K retrieval, which means, for example, you have champions list, all this stuff. Tiering, K-grams, for example, for wildcard queries. And then you have a part which is devoted to scoring and ranking. We have seen one way of doing scoring and ranking, which is based on relevance only. Actually, we have just hinted at the fact that scoring is also based on some static score, which we still have to define in some way. Okay? So just remember, this is one way, a very high-level block architecture of a system. Yeah, I will give you details about the resources. Now, the next thing we can do, I'm undecided. Well, no, I have decided. Let's see where it is. So, I will make this code available, of course. This actually I made last year, and just wanted to give an idea of how actually you have many of the resources available that you need in order to do a few of the things that I just showed. For example, let's assume that we want to collect some web pages, and we want to be able to answer queries on that collection, on the text of that collection, using cosine similarity to find the most relevant documents, given a query. What can we do? Actually, most of the stuff is already there. You have seen a part of this stuff. I'll just show you how you can proceed in Python. Okay? If you have another language, there will be other libraries most of the times. You don't want to proceed in C, probably. But you don't need. So if you want to have, what is the most stupid way to have, to collect a collection of, to collect web pages? Well, for example, you use wget. You know this? So wget, where is it? Wget, this command here. Well, of course, it's not going to work now. It wants a URL. If I issue, let's see if Marcello gets angry. I will stop it because let's see if it is going to work or if it wants, yeah. For example, I just downloaded the index page of our website. Okay, you can do this recursively. It will do it for you. Be careful with recursive because your collection may grow very large pretty soon. Okay, so you have collected some web pages. Now the web pages are on your machine. For example, here. Let's see what they are. No, why? Waiting for DIAG. Home Becchetti. Ah, yeah. They are seminar announcements. I collected, we have a lot of seminars, so there were enough pages to download. Now you have some web pages. Now, actually, if you look at these web pages, they contain a lot of stuff. You know, nowadays web pages contain text. They have different zones or fields, as we have seen, that we might use. I'm not going to use this, but we might use them. And then they can have scripts, for example. All this stuff, if you want to do cosine similarity, is stuff that you may or may not want to get rid of. For example, if I want to do cosine similarity, scripts I don't want to have, right? So, downloading the pages, done. Or you use some other libraries in Python, for example, if you really want to have a crawler, if you want to build your own crawler. Actually, in that case, you will just take one of the dozens of available ones, okay? Then, once this is done, you have these documents and you want to represent them in some way. So, this code starts assuming that I have my collection available. What are you going to need? Let's see. Some of the things are already, you have already seen, I think, with Professor Vitaletti. So you want to do stemming, perhaps? Actually, okay, I didn't fix this, but probably in this case, lemmatization would be enough. For example, removing plurals rather than finding stem. So stemming, sometimes it's working actually worse than without it. So, you know? It depends. In some cases, it's better to have stemming. In some others, it's not. When is it better? Well, hard to tell. Depends even on the language sometimes. Okay? But let's say this time we have stemming. Then you want to tokenize. You want to find, actually, first tokens, then stems, right? Well, globe is just something that I need to explore directories in Python. It's nothing to do with. And then you want to have your TF-IDF scores. Do you need to build them? No, never, unless you have to do. Okay, so you just check around and you say, I want to have TF-IDF, no. TF-IDF, let's say Python. How to process. And you check this and perhaps, then you need to see, scikit-learn feature extraction, TF-IDF vectorizer. Let's see what this is. And you get everything. Okay, the string, what it is doing, the parameters. And actually you find many of the things we have just seen. I mean, it's in scikit-learn they apply very scholarly the techniques that we have seen. Probably they are using the same textbook. I'm not kidding, probably, okay? The vocabulary and so on. So, and then they give you examples, all the methods you can use, very, very useful. Now, at this point, good, we have found what we need, so we will actually use this package. And then, do we need to compute cosine similarity by hand? Of course not. We have another package, scikit-learn metrics pairwise. Actually, it's not, there are other packages that will provide this stuff. If you're using R, you will have similar stuff, okay? Or even other, I guess you have similar stuff in pandas, which is another Python package. Many of these things you find in other packages. And then we are going to use, at some point, some, to do sorting. Since we are very lazy, we are going to use, we want to sort and then find the indices. And so we are using, let's say, a function from a NumPy, the NumPy package. So what are we then doing? First of all, we'll need, well, first of all, we import all this stuff. Then we want to stem the text. So we will define just a function that is doing, sorry, no, that's correct. We want to do stemming, right? So we define a function that will do the stemming. You give it a text, and what you get is a string of tokens, or stems, actually. And then we decide to use Porter stemma, for example. Then we know which is the path, the docs. We build a dictionary of documents. That will be used because the dictionary will contain for every document, for example, we will use that at the end. But anyway, it's more or less clear what I want to do, right? Every document, the documents will be represented as a list of strings. Okay, they are short documents, I can do that. That's one of the ways in which you can invoke TF-IDF vectorizer. You can invoke it in many ways. One of the possible ways is a list of strings, and every string represents your document, okay? In this case, I mean, if you run this as a Python script, you will have an argument that is the query. Otherwise, in this case, I'm using Notebook. I didn't want to pass arguments to Notebook. There is an involved way to do this. So I just gave a static query. Statistical randomized algorithms. Wow. Are we going to find anything? No. What did I do? Good.
In the previous block, in the previous block where we stemmize the words, when we combine both.
Which one?
Second one, yeah. Line, no, both. Yeah, there. In line 2. When we define this team text, why do we put we put a space? The plus double quotes, it means just a space, right? I mean, I don't know why we create an output in that way.
It's a string, the output. So I'm tokenizing a piece of text.
Okay, and then I split the
I get another string, a string of tokens.
Okay.
That's all. I add a string of words, and I get a string of tokens. Okay. Of stemmed tokens, okay. Of stemmed words. Nothing more. Okay. You just need, I mean, if you want, when you apply this, you can give as input a document and see what you get in response. Okay? I'm not doing it now, but you can try it yourself. So you just give it a piece of text, and you apply word tokenize, and then you see what you get. So we went over this now, and this is essentially all the code, actually, and we are done. So let's see what this code is doing. Well, for filing globe my path, blah, 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 this means simply the following. My path is the following. My path is this path, okay? So it is relative to this directory, and It is just this path, so pages, and I'm asking Globe to proceed recursively. That's all. So for every file I find, I know already there are only HTML files there, so each of them is a document. So I recursively go down this directory, and I process every document, nothing more. Essentially, what I'm doing here is that I'm creating a dictionary in which every document, so I associate the document, the name of the corresponding document to a file. That's what I'm doing. Because later on, I will get the most relevant document for a query will be, I don't know, document 6474, and I want to know where the document appears. Every document will be represented by a vector, so eventually I will have a matrix, a word, a document term matrix, okay? So my indices refer to the rows and the columns of that matrix, and I need to know which document every row corresponds to. That's all. So that's all I'm doing here, okay? I'm associating the file to every row of the future matrix, the name of a document. That's all I'm doing. And then I open the file. For each file, I open the file, I pick the text, and I apply this beautiful soup. What is beautiful soup? It's a library to process HTML pages that contains a lot of beautiful stuff. Among this beautiful stuff is methods that allow me to scrap away scripts, strange metadata, and so on. Because I'm going with the idea of just using the body of the text to compute cosine similarity. If you want to do zoning, you're not going to do this. You have the possibility to single out different areas of the web page that you want to process separately. Okay, you can do that. But in my case, I was just looking for I want the body of the document. That's of the text. Once I do this, for example, if I print this document, what is the first document? You see what I get, just the text, nothing more. At this point, I do all the stuff I need. I compute cosine similarity. So in particular, so it's clear that you should vectorize documents once and for all, and not at the end. Okay, so the query is submitted online, the vectorization of documents is done once, of course. But in this case, it was not important since the query was embedded in the script. Okay, so essentially, I invoke a TF-IDF vectorizer, I build a vectorizer object, and then I transform the set of documents. So remember, this is a list of strings. This is transformed into a matrix. Okay? Nothing more than that. Then I do the same for the query. And then I apply cosine similarity. This is applied to the set of documents, so to the matrix corresponding to a set of documents, and to the vector, which is a special case of a matrix, corresponding to the query, right? What is cosine similarity doing? Cosine similarity, if you give cosine similarity to matrices with the same number of features, it will compute all pairwise similarities. In this case, it will just compute the similarity between the cosine similarity between this vector and each of the vectors contained in this matrix. Each vector corresponds to a document. So eventually I have the result, which is a vector of cosine similarity values, one per document. Since this is a NumPy object, I will use a NumPy function to do the following. I will first sort the results based on cosine similarity. So the higher the cosine similarity, the lower the position of the document. And I do this using argsort because I want the indices back. So I want to know what is the index of the matrix which corresponds to the highest cosine similarity with the query. and I do that using arcsort. Once I have done this, I use the dictionary to see which is the document that corresponds to that index, and I print it. If I do this, I get this page, 6618. Let's see what it is. 6618. Where is it? 6, 8. Where is it? There it is. Let's see what it is. Ah, that's it. This seminar by Eli Upfall. I can tell you, if it is a seminar by Eli Upfall, it is related to the query. Okay? Just to be clear. Actually, in this case, it's relevant because the terms we were looking for appear in the title. So you can be sure of that. So you can try this with several input queries and see how it works. You can improve the code and so on. I'll give you the entire package. Okay? And then you feel free to improve my poor piece of code. I mean, it was nothing. It was just something I did fast, and of course can be improved in a myriad of ways. Just to give you an idea. Okay? So you can really do these things, of course, at a basic level without much effort, so that you can practice the principles you get in the course and from the book. Now, we were fast, so we can just skip to something new at this point. Let me see. Ah, no, I have got them here. I didn't, have you? Yes, you have questions. Good.
What is the best way to store posting list? And
What is them?
the best way?
I had no posting list here. Okay.
And dictionary, I mean, in secondary memory.
Okay. So in primary memory, you're using a dictionary. Implemented, you will have a hash table and so on. In secondary storage, how they do this exactly, I don't know. I should explore better. But let's say that in a secondary storage, so you have a link structure. No, normally what you have, I can tell you what they do at an abstract way. I guess you have seen this with Professor Vitaletti. Normally you have some associated to each posting, you actually have a pointer, what is called a pointer, that allows you to access a specific area of the secondary storage, right? That's what you have. How this is done in practice? Well, I mean, I'm not a system manager. And actually, to tell how it is done in practice is not trivial. Very often it is ad hoc systems designed internally, you know, not public. But I guess there is a way. I'm pretty sure what you can do is probably you access some publicly available search engine. There is a number of free ones, and I guess you can download the code as well. Okay? I can give you pointers. For sure there is web crawlers, but I think there are also a web search engine that can be used freely, and whose code is publicly available. If people are interested, I can ask some friends that are experts in this stuff and probably give you pointers to this part. Okay? Other questions?
Just one regarding the
tiering.
Yeah, I do not understand if that is an alternative to tier or
No, it is a way of tiering. You can tier in different ways. For example, in this case, we're assuming that the posting lists are organized, are split, are partitioned among different machines based on the terms they refer to. So you are splitting by terms. Sometimes you can split by documents. What does it mean, splitting by documents? It means that regardless of the terms they contain, certain documents are on a certain machine, other documents are on a different machine. In that case, whenever you issue a query for one term, you submit it concurrently to all machines. Why are you doing that? Can you tell me? Have you understood the question? Okay. So this is one way of splitting the posting list. How should I say? This is a horizontal way of splitting. So each term appears only on one machine, and you have the entire posting list for that term on that machine. Another way of organizing tiering is doing the dual of this. So every term can appear in different machines, but each document appears only on one machine. You see my point? For example, so you could have T1 on this machine and say on this machine. In that case, you would have one partial posting list for T1 on this machine and the second posting list for the same term on this machine containing disjoint subset of the document, doc IDs. Okay? Is it clear? For example, half of the posting list for T1 here and half of the posting list for T1 here. Okay? So this is called document-based tiering or indexing. In that case, if you're looking for if you're looking up some term, for example, T1, you issue your query to all the machines at the same time, in parallel, because part of the posting list is here and part of the posting list is here. Why are you doing this?
If a traffic tier is easy, we can access to other tier.
You can do this concurrently, right? So, concurrently, yeah, in parallel, not concurrent, sorry, in parallel, really in parallel. So you're exploring, I mean, it's like exploring the same posting list but faster, yeah? Also this is faster. In this case, what you're doing is you're collecting different posting lists at the same time. In the other case, you're collecting the same posting list in parallel. So you're speeding up collection of one posting list. Okay, it's two different ways of doing things in parallel. And these two ways are actually widely used. And they are, an alternative is the type of tiering that we were seeing before, having more level tiers depending on the impact of documents for different terms. Yes?
But all the machines contains all the terms that are present.
In which case?
No, it's a question.
Yes. Everything nowadays, the posting list, not the documents collection, only the posting list, the postings. So the snippets, how do you want to call them? They are contained, actually the snippets are normally built at, the result page is built at runtime, on the fly.
With a elaboration in parallel with the...
I mean, as much as you can. Okay. But anyway, yes, the posting list event nowadays are contained in the main memories of the machines. Normally not just one machine, a number of machines. Okay? Yeah. Then you have geography, then since web search engines are global, you also can have split among different geographical areas and so on. So, what can we see next? I would say, I was undecided, actually. I wanted to begin something completely new. But let's say that this is important. So I think this is the right next topic to address. So this year I also would like to do something about recommender systems. Because did any of you take the course in data mining? It was the first semester. Yeah. No, the first, yeah? Was Aris doing the recommender systems? He did recommender systems, collaborative filtering, collaborative filtering. What does it mean a bit? How many hours?
Just the mechanism. Just the mechanism. So I think just one lesson.
One lecture?
Yeah, one lecture.
Okay. Okay, I could tell you a bit more, perhaps. Just on collaborative filtering. But because that's useful for the future. Okay, but before we talk about collaborative filtering, so Amazon and friends, maybe we should say something about how you evaluate a system. Okay, so evaluating a system that is providing you objects in response to a query, it's a philosophical matter in the end. It's not an easy thing to do. Let's try to make sense out of this. I mean, this is a very, very important area in information retrieval in general, not just web information retrieval. So I'm going to spend some time, this lecture and the piece of next lecture. But it's important to have, yeah, okay, this is not my example, of course, but it's a nice example, so it should stay. Now, someone comes to you and tells, look, I have a search engine that is fantastic. It's performing beautifully. And now I'm the chief of operations at Nozama, and I say, what should I do? Should I just believe Sergey or whatever her name, or should I just say, That's a tough question. I mean, it's a central question. So, because it has to do with the way in which these systems make money, right? So, in the end, a search engine, unless it is DuckDuckGo or something else, normally has to live out of something, you know? You know, Google is expensive. It is not just, you know, some fun for someone. It needs a lot of money. Amazon the same. Well, Amazon is a bit, you know, Amazon is selling stuff. So, but Google or Facebook or whatever, what are they selling? So in the end, some of the things you are selling is the possibility at least to do advertising. This implies that you, how should I say, you create a convenient environment for advertising. For a search engine, this means that, for example, your performance is good. So very often you make people happy. Okay? For a search, let's consider now a search engine. For a search engine, what does it mean to have a good performance? Does it mean to be fast? Also. I mean, we want a result page within half a second, roughly. Otherwise, we are not happy. It means to return relevant results. Yes. And there starts the problem. What does it mean, relevant? So what is performance? Assuming that the efficiency of the search engine is good. I mean, it is fast. Okay, are we done? No, we are not done. This is just a necessary condition to be a well-performing search engine. But what does it mean to be performing well? That's the question. This looks like a simple question, but it isn't. Right? So going back to this funny story, you could say, okay, you say you have a very nice search engine, how fast is it? And that's the first question we were asking. But then you could ask, does it recommend related products? So related products, this is already something more in the direction of recommender systems, and has to do with the notion of proximity within objects in some feature space. I mean, we will try to say something more about. But what is the quality of my search engine? So what does it mean to measure the quality? In the end, you know what it means? That I'm happy with the results I get. Now, measuring how an unknown user, unknown at the other end of the world, is happy with the results you provide is not very easy, you know? I mean, there is no way to go and ask. He would like to do that, but So you need some proxy of users' happiness. For example, if you notice that search results are clicked a lot, which you can know, because if you have noticed, you click on a search result in Google, and normally it is not that that link is not just a link to the document, to the original document, it's actually a link to a script, which eventually redirects you to the document. That script is, among other things, memorizing your click. Okay, so it is at least remembering that user with ID number 635-227 clicked on this link upon searching, upon submitting this query. Everything ends up in a query log. All the things you did. Okay, even if it doesn't know your name, you're there. So, other indirect ways of understanding is whether or not users buy after doing a search. I mean, this can apply. This does not apply to every scenario. For example, how would Google know whether you purchased something upon submitting a query? So very often you're just submitting a query for, I don't know, the last episodes of whatever, True Detective or whatever, right? So you're not purchasing anything. For Amazon, this is a bit more related, actually. But in general, it's very hard to tell what people are going to do once they submit the query and get the result, unless they buy online. Okay? Then you can try to track returning customers or returning users, which search engines actively do, using cookies, essentially. So there is a number of ways in which you can get indirect information from the users. And I hope this year we are going to see a number more which are used to do online advertising. So, but happiness is an elusive notion and very hard to measure. So there is some people who started investigating the matter. And even to build the first data sets in the Cranfield experiments, I mean, this is what data set is still available. Normally, what we try to use is what is called relevance of search results with respect to what? To the query? Let's say with respect to the query for the moment, but that's actually not the truth. That's not the truth. But so the first step is the following. Okay, users' happiness, we cannot tell what it is. So, oh, sorry, there is a mistake here. Sometimes the English fails me. So, we go down from happiness to something that we hope to be able to measure, which is relevance. Based on past work. So at some point you decide, happiness, we cannot quantify, come on, let's be serious. Let's try with relevance. I mean, we have an intuitive idea of what relevance is, right? If I'm sitting here and issuing a query and receiving an answer, I can tell whether or not it is relevant for my query. How do I know that? Let's make an example. I really want to make an example with you. Okay? Let's go for this example. This is my query, right? So these are animals, I guess. Leopard, National Geographic. So the first pages are about facts about leopards, and so on. Am I happy with the results or not? Can you tell?
It depends on your initial on your intention of what were you find. Maybe you were looking for like the Apple operating system they were.
This is a simple case. Maybe I was looking for this. Okay? So this is a very extreme case, actually, in which the term I was inserting in my query, leopard, is polysemic. It has different meaning. It can mean an animal or a tank. So this I just wanted to give you an idea of what I'm meaning with an extreme example. Very often it is not like that. But for example, I gave this issue, bath detergent. Okay, that's my query. So you would like to return documents that are relevant to the query. Is this correct? Is this really what we want to measure? So relevance with respect to the particular query. The point is that there is a number, a query is a couple of words very often, 3 words, not so many. But behind there is a human having something clear in mind. So she wants something, and she tries to express what she wants in terms of a query. And also, the query might be, how should I say, the query itself might be better or worse at retrieving good documents, depending on the underlying search engine system, based on how good the user is in translating what she has in mind into a few keywords that will make the best out of the search engine. You see the point? That's, this is not a trivial matter. And I have lost my, okay. Okay. So very often, actually, what people say, what people do, is not considering a document relevant to a query, but they try to measure relevance with respect to the intent. What normally is called the intent behind the query. So, trying to understand what the people really had in mind. Okay? Is it clear? Oh. So, eventually, if we want to measure the effectiveness of our system, we'll have queries submitted by humans and documents. But what we are trying to maximize is the relevance of the documents with respect to the intents behind the queries that were submitted. How are we going to do this? And in general, how are we going to test, assess the performance of a search engine with respect to retrieving relevant documents for queries? Let's see which are the ingredients that we know. I'm being slow in this part, even though everything seems obvious, because it is less obvious than it seems. So actually, it is useless to set up a complicated system if you have no clue, no idea of how you are measuring its performance. If you don't know where to begin when it comes to the point of showing that your system is actually performing well. Is it clear? So that's a key issue in information retrieval. So we should be careful with it. There is a few things to know and to reflect upon, but we should be aware of what we are doing. So let's try to see what are the ingredients. So let's go back to that funny story. So Sergey, so he comes with a search engine. We want to assess the performance of the search engine. Let's say that we make a test and we see, good, the search engine is fast. Engineering, let's say the architecture of the system is well performing in terms of time, complexity, and so on, use of resources. Now, we want to assess the performance of the system in terms of user experience. Is this going to retrieve relevant documents given a query or not? Let's assume for now for a moment that we know how to measure relevance of a document with respect to a query. Okay, let's say we know that. What do we need to prove? So what are we going to ask from Sergey to prove that his search engine is performing well in terms of relevance? What do we need?
The user interaction with the system. The user interaction with the system.
No, I'm speaking in practice. What does Sergey have to do?
Insert a query.
Huh?
Insert a query. Insert a query and show us the results.
Are you happy with that? No, I mean, the basic operation will be issuing a query and providing us with the results. Then we sit together and I will tell, for this query, well, okay, this is the basic operation. At some point, a query will be issued and a result page will be read. Fine. Let's try to make this a bit more, let's try to do this as engineers. You want to prove something.
We can try to measure out how many times in a limited time a certain user typed similar queries. If
Again?
we can measure how many times in a limited time certain users type similar queries. Not the time the user types the queries, less the engine is precise.
But that's the very point. I mean, how do we measure this? Let's put it this way. We are not going to write theorems on these things, okay? I mean, that's not the type of things where you write theorems. I mean, in order to write theorems, you need to do some modeling. But let's say, so one way is the following. I have 1 million users issue queries. Then there are documents returned. Every user will be happy or not. I interview each of them. I mean, I do this in a scientific way, not just some random. No, I need some confidence in the results I have. So I don't know. I pick 100,000 random users. They submit queries, and then I interview them and I ask them, so how do you like? Which was the most relevant document for this query? I give you, I don't know, 100 documents in some order. And then I ask the user, okay, this is the query you issued. Please sort the documents I gave you according to order of relevance. Then I check the order in which I returned those documents and compare it with the order that the user considers to be correct. You can do that in principle. Are you going to do that? Come on. It is never, who is going to run such an experiment? Okay? So, we need to have something which is scientific sound, but at the same time which is manageable. And above all, reproducible. You know, in science you want to have reproducibility. So at some point you publish a paper in which you claim that your search engine is the best ever in terms of relevance, but if I'm not able to reproduce the results, who knows? In the end, the only way I will have to measure is the amount of money you make, right? But it's not a good technique to select new strategies. Nice strategies, when they appear, there is no money behind. So, what can you try to do? You can come up with what are called benchmark collection. What is a benchmark collection? It is a collection of documents, in our case, that is used as a data. It's a data set, essentially. It's a collection of documents about which we know everything. Okay, there is a number of famous benchmark collections that are used by computer scientists in order to assess and to prove performance of the algorithms or let's say of the approaches they propose. Then we need also a benchmark suite of queries. Why? As I was telling you, the idea is always that we are measuring the relevance of a document with respect to a query intent, so what the people have in mind, and not with respect to a query itself. You know, the problem is that I could do the following. I could have a benchmark collection of documents. That's relatively easy to get, right? I mean, I collect, it's easier to automatically collect a collection of documents. You see? I can do that in many ways. The problem is having a meaningful collection of queries. Why? Because I could, for example, randomly generate queries. But are these queries typical? Do they really help make a connection between the query and the intent behind the query? Okay, so I want a benchmark set of queries that really, where people really, how should I say, where the connection between the query and the intent behind the query is clear. Okay? So I will be happy with a subset of all the possible queries, but at least a subset that is sound, that makes a lot of sense. So it's a bit what you were saying before, right? Try to understand what the people have in mind on the typical query they ask. You cannot do this at a scale, but you can try to have a team of people working on this. And it is, for example, what some organizations have been doing over the recent past. Once you have found this, a nice benchmark collection and a benchmark of queries, then you need an assessment of whether each document is relevant for each query or not. Yeah, it's a subset of the queries, set of documents. Maybe the documents are organized into topics in some way, and you consider also queries as organized in topics. That's normally what is done. But then, if these are the queries for a given topic, and this is a corresponding collection of documents for that topic, you will have to take whole pairwise relevance values. Okay? That takes a lot of time. And how do you measure this relevance? Normally, this will be let's say, I'm speaking of what? I'm speaking of all the necessary infrastructure to prove the effectiveness of an approach. Okay? So this is the data set. I'm speaking of a data set to use as a benchmark collection. So we need the queries, we need the documents, and eventually we need what I told you last time is the ground truth. So we need some human assessors, human judges, to tell us, to decide whether a given document is relevant or not for a query. Okay? Normally this will be a binary value, relevant, non-relevant. Sometimes you can ask the users to give I don't know, 1 to 5 stars to measure relevance. Okay? But let's take it is a binary value for the moment. So once you have all this, then you have a benchmark collection. And then you can ask Sergey, okay, Sergey, now, I give you this document collection. I will issue this, I don't know, 50 queries. For each query, you will return me 100 ranked documents. And then we will see if the ranking of the documents reflects the ground truth, which I already know, decided by human assessors. I remind you once more, normally we take the ground truth to be what humans decide. And again, normally, you have 2 ways to decide whether or not a document is relevant to a query. Either you ask an expert, or you ask more than one person, and then you have sort of a voting scheme. Okay? There are even trying to satisfy certain indexes of quality, certain thresholds of quality on agreement. Okay, so it's not an easy matter to do, but there is, let's say, people doing econometry, statistics, sociology, they have come up with a number of more or less rational approaches to do this. Okay? But just to let you understand that this is far from an obvious matter. Now, you have a number of collections which are available. One of the most used one is the track collection, which contains typically documents, relatively short documents, collect on a given topics, a collection of queries for the topic. And the process of, for example, selecting the queries is actually one of the most complex parts. Normally, in order to select queries, initially you generate, I don't know, a number of hundreds or thousands of queries for, divided by topic, and then you ask human assessors to decide whether or not they are able to understand what is the intent behind the query, so what the people had in mind. So when you create the query, you know what is the intent, and then you ask people to say whether or not they can retrieve the intent, whether they agree on which is the intent. When this is the case, then the query is accepted. Otherwise, it isn't. So you see, it's a very, very complicated procedure. But so, of course, when you do this, you have a benchmark collection, so you can perform experiments with respect to such a collection, which can be reproduced. That's a necessary step. Can you avoid doing this? So, let's go back to Nozama. If you, in principle, you could try, for example, Amazon can leverage the users, right? So, Amazon actually tries to leverage users because you have users and you can have some indirect measures of happiness. For example, I buy a product or I buy it again. If I buy it again, I mean, that's like saying I was happy with the product, right? It's the same. Or, but in the end, or sometimes they just ask you to give your opinion, to rate an item you purchase, okay? Google, for example, cannot afford doing that. It cannot contact users to ask, what do you think of this? Amazon has a database of users. Google hasn't, okay? It has just a database of identifiers, which is not the very same thing. So, but even if you have all this information available, and let's say you have a collection of possible queries in the order of the tens of thousands, and you have, I don't know, 5 million products, you know what it means? Every user, every product. Come on, can you think of this matrix? No, you don't want to represent it, okay? That is our first reason to have a benchmark collection, okay? Yeah, you do the math, but I guess you believe me when I tell you that you don't want to implicitly or explicitly build this matrix, okay? Also, there is an issue. You know, sometimes people think, okay, we can use, nowadays there is crowdsourcing, you know? Amazon Web Turk, yeah, Amazon Mechanical Turk, sorry, or this type of things. You submit, I don't know, a collection of web pages, a collection of queries, and you ask people to say whether or not a certain query is relevant, a certain document is relevant for a given query. That is also another way to build benchmark collections. But you pay. That has a cost. And also you have to rely on the online platform about, how should I say, the expertise of the human judges, which is not always the same. Now, just to summarize what we have seen so far, first of all, what we would like to measure relevance with respect to is user need or user intent, whatever, however you want to call it. In practice, we translate it into a query, and that is the reason why when we build a benchmark collection of documents, we are so careful in selecting a subset of queries whose intention is clear, which have a clear connection between, where there is a clear connection between query and the intent behind. Yeah, like this. You see the problem? Your information need, which is what the system wants to know, it's not the same as the query you submit. This is just a brief summary, pool cleaner. What did I really want to do? Who knows? Okay? So I will try to measure some relevance with respect to this query, while what I would like to do is this. So the only way to really have a measure of how relevant a document is for this intent is to have a collection of sampled queries where this connection is very tight. Okay. So now that we have the basics, we can go to measure of precision. So now, from now onward, you have a benchmark collection of documents. You know everything about the document collection, because this document collection has been, let's say, processed by humans, okay, who spent a lot of hours, a lot of time. Each of them perhaps 100 people who manually gave relevance judgments about documents for given queries. But you do it once, you know? Now, you know this? Who has never seen this before? It happens. Come on. No precision? No recall? Yes or no? Yes, you have an idea. Yeah, I mean, if you took some other courses, you may have an idea, otherwise not. You have an idea? Who has no idea? It's just, I just need this to tailor the explanation, not for, I'm not going to judge you. There is nothing to judge, otherwise I would not be teaching this. Anyone who never heard, who is hearing of this for the first time? So you heard of it. Okay. So, let me see. Okay. So what are we interested in here? Now we want to measure relevance. Given that we have a collection of documents, then we have a query, and we know which documents of the collection are relevant for the query, because we are doing an experiment. Okay? Now, what do we want to know? Let's assume, for example, that our search engine returns 5 documents for a given query. Okay? Why 5? I mean, it can be 10, but we know we are not going to move far beyond 10 documents, right? So let's say I return 5 documents in response to a query. What do I want to know, more or less? Is some measure of how many relevant documents I retrieved, right? So let's assume that these are my documents. Consider that when I return documents, I will return them in some order. So let's say this is the ranking. So this is, for example, the top document in the results list. The one you see first, this is the second, and so on. Now, let us assume that this document is relevant for the query. This is relevant. I'm just speaking of binary relevance here. And that's it. Am I doing well or not? How am I going to measure this? So let us try to see. We can, when I try to measure this, there are 2 ways of looking at it. I could ask the following. I mean, they correspond to different questions. The first question is, the documents I'm returning, are they relevant? To which extent are they relevant? So in this case, I focus on the documents that I am returning, and I want to know how many of them are relevant for the query. This is called precision. And essentially, it is measuring which fraction of the documents I return are what we call true positive. What does it mean? It means that it's documents that should be returned and are actually returned by the system. How can I measure this? Well, since I'm just returning 5 documents, I can consider the fraction of them which are relevant, right? And this corresponds to this. The number of true positive, in that case 2, divided by what? The total number of documents I returned. These consist of 2 types. The first one is the true positive. Oh, this will be a true positive. The second one is documents that are not relevant, but which I return. Right? How can we call them? False positives. I mean, why? For the system, they should be returned, but actually, in truth, they should not be returned. So let's call them false positives. Of course, TP plus FP equals the number of documents I return. And that's precision. But there is another question I can ask. Here so these documents come out of some collection here. So these documents, for example, these documents come from a collection that contains both relevant and non-relevant documents, right? I can ask the following question. Well, this document collection contains a certain number of documents that I should return, which are all the shaded ones, 4 in this example, and I return, in this case, 2. So the fraction of relevant collection I return, the fraction of relevant documents that I return is 1/2. So in this case, I'm measuring something different. I'm measuring how well I do with respect to how well I could do. Okay? Very often, what happens is that we call this recall. This is the fraction of documents that, this is the fraction of relevant documents that you actually return. Okay? Very often relevance in a real search system cannot be too high than a given threshold. Why? Because, for example, I will just be returning 10 documents at a time. So if I have 1,000 relevant documents, I'm in the best possible case, I will just be returning 1/100th of them, right? Okay? So, but anyway, what is recall? So recall is, again, the numerator is always the same, the number of true positive. In the denominator, I'm putting something that does not necessarily belong here. I'm putting all the number of the total number of shaded documents or relevant documents that I have, and which for this reason I distinguish in 2 types. So the true positive, which means documents I should return and I actually return, and the false negatives. Negative because I don't return them, false because they are not negatives, actually. And that's the definition of recall. Okay, this is the key definition that you use. It's a key definition, and let's say if just used in this way, it will not be of so much of help, because in a ranking system, because how should I say? Well, one of the reasons is just that I'm just returning a fixed number of documents, and also the positions of the documents are not equal. So, for example, returning a relevant document in this position is more important than returning a relevant document in this position, because the user is typically going to see this, surely, but this may be. You see that? So there is also an idea that relevance should in some way be related to the ranking of the documents. So yes, there is if you have troubles remembering how to tell, I mean, people sometimes confuse recall precision. if you think them in terms of conditional probabilities, it's clear. Okay? Yeah, I mean, it's a statistical probability. It's not a true probability distribution. It can be defined as a statistical distribution. So, essentially, if you think about fraction of retrieved documents that are relevant, what is it? It can be seen as the probability, assume that you retrieve something at random, appear random in that result list, is the probability that a document is relevant provided that it is retrieved. Why? If you were to define this probability, you would take the intersection in the numerator and the number of relevant documents in the denominator. So that is why this is another way of indicating it, of indicating precision and recall. I don't like it very much. I mean, for me, probabilities are serious things. So I don't like these games, but still, you can find them. Is it clear so far? Good. Now, we are almost done. Let me see. Yeah, we'll only see precision at K, and then we stop. So that you know what I'm doing soon afterward. So, how do we make the thing that actually the position in which relevant document appears in the ranking is important? We use normally an extended notion of precision, which is called precision at K. Precision at K accounts for the fact that you just return a fixed number of documents. So, for example, if you want to know what is my precision at 3, means what is the fraction of relevant documents which appear in the first 3 positions. In this case, it would be 2/3. These are relevant and these are non-relevant, okay? And so on. And you can do the same for recall. In particular, for recall, it makes a lot of sense. Also, I mean, what does it mean to do it for recall? Actually, in this case, there will be no clear distinction. How are you going to measure recall? I mean, if you're just considering the first 5 documents, that's your budget of document. In that case, if you just say the fraction of relevant documents with respect to the 5 you have returned, the 2 definitions collapse. Okay? So in that case, you're essentially taking the number of documents that are relevant in the first K positions. And you typically repeat this for every K. And then you have a precision recall curve that evolves with K. Okay? It is not clear that it's growing. I mean, it can be growing, or actually it's going like this. Okay? I think I'll stop here. This is a good place to stop.